we define power as the rate at which you can do work. So that's the time derivative of work. If you want to consider some discrete time interval, delta t, then you can say the average power that's being exerted over that time interval is the amount of work that's done, the change in work over that time interval, divided by that time interval. And then take the limit as that time interval gets very small, and that gets us back to our instantaneous power dw dt. It has units of work per time, that's joules per second in SI units, which we define as watts. 1 watt is 1 joule per second. You might be familiar with horsepower in some cursed units used in the land of the free, called 1 horsepower is 746 watts. So that's a conversion. Use horsepower if you'd like. I will be using watts and kilowatts and those sorts of things. There's a relationship here, actually, to velocity, where we can say your power, since it's dw dt, we can substitute in for our definition of work that says that my work is f dot dr, so dw is f dot dr, and then we can put that dt with the dr and call this f dot dr dt, where dr dt is your velocity. So your power is also equal to a force dotted with a speed of motion, power and velocity. Let's do an example to see if we can do something useful with this. How much power must an automobile expend to move a 1,200 kilogram car up a 15% grade at 90 kilometers per hour? Assume that 25% of the power is dissipated, overcoming air resistance and friction. Lovely. Let's do a free body diagram. I'm just going to do it right on this car. Weight is acting downward. We have some normal force that's acting normal to the surface. And we have some force that our car is exerting on itself, putting it out through the wheels, using friction of the wheels to try and climb its way up here. We have an angle, theta here, that we know. It's a 15% grade. Okay, we have to figure out what a 15% grade even means. Let's try that. 15% grade. So 15% grade means that it's the angle that will give you for every 1 unit that you move horizontally, you move up 15% of that. So we can say that that angle is equal to the inverse tangent of 0.15. So if you've ever seen those signs that say 15% grade, danger, trucks, whatever, now you know, you can figure out the actual angle that that corresponds to. Here, that's 8.53 degrees. All right, we have an angle now. Here, I'll just put the theta down there. What else do we know? We know that it might make our lives easy to establish some coordinates that are aligned with our incline, which then makes me inclined to find this angle here, and it will be using similar geometries we've used in the past. That angle theta of the incline is the difference between that normal to that incline and a vertical line. All right, I think we've done our free body diagram of the car. Now we can consider the force that we get from that car in order to drive our way up here. We will sum our forces in whichever direction is useful, let's say the x direction. This gives us my force is pushing up, and my weight is what makes this hard. So the weight times the sine of that 8.53 degrees. And that's the only thing pushing against me, and this will equal mass times acceleration. If we're trying to accelerate up here, then we might need more force. But if we're just trying to move at a constant speed here, then we can say that this acceleration can be 0, and we just want to be moving up this incline. That gives us a force that's equal to my mass of 1,200 kilograms times gravity times the sine of 8.53 degrees. All right, So far, so good. Now we can use that definition of power and see if we can figure out how much power we need for this. We'll remind ourselves that that power was F dotted with V. That seems to be the most useful one to use right here because we have our force already and our velocity is we're traveling at a constant speed. And that's also why we said that our acceleration was 0, because we have the constant speed we're traveling at. That means acceleration is 0. Let's go ahead and say that that's the power we need. If we're assuming that 25% of the power is dissipated, then we can say that the total power we need is going to be 75% of the total power will give us this power. So we need more power because 25% of whatever this total power is getting dissipated. So I'm taking care of that by multiplying by 75% there. All right, so now we get the F dotted with the V. The velocity is in this direction. Let's draw it in just to have it. My velocity is in the same direction as my force. So the dot product gives me a cosine of 0 or just 1, which will then be mg sine 8.53 degrees. So that's my force. My velocity is 90 kilometers per hour. And I think I might want to unit convert some. So from kilometers, we'll get to meters. 1 kilometer is 1,000 meters. And from hours, we'll get to seconds. 1 hour is 3,600 seconds. If you don't know that one, you can do 60 minutes in an hour and 60 seconds in a minute. So that'll get us the right unit conversions. And then cosine of that 0 degree angle, which gives us 1. All right, we now divide by 0.75 on both sides, and now that will tell us the total amount. So in plugging this in, I guess I'll write some more numbers here. My total power ends up 1,200 kilograms times my 9.8 meters per second squared times the sine of 8.53 degrees times what we get from this, which is 90 times 1 over 3.6. So 90 times 1 over 3.6 to get us to meters per second. Here we can even cancel out some of these. Kilometers cancel. Oh, meters don't cancel. Hours cancel. There we go. So we have meters per second. And then divided by the 0.75. This is part of why I don't plug in numbers earlier, because I end up having to rewrite the numbers with units so much. It's way easier to just write a single symbol instead of the whole long number. All right, 58 kilowatts. It also makes it more likely that I make transcription errors when I write more things. All right, 58 kilowatts. Lovely, we did the thing. Go team. That's in reasonable units. If you want that in nonsense horsepower units, because you know horsepower as it relates to cars, here I'll show you. I'm a giver. 1,000 watts per kilowatt. And then we can use the horsepower conversion of 746 watts per horsepower. So do that if you'd like, and you can figure out how many horsepower this car needs in order to travel up this incline at 90 kilometers per hour.